The battlefield is changing, and while the U.S. has been focused on insurgencies in Iraq and Afghanistan for nearly 2 decades, our adversaries have been working tirelessly to catch up to our warfighting capabilities. It's just a fact. The gap is shrinking, and there's a lot at stake.
You know, the world is changing. We're in a very dynamic environment. We're taking various actions in response, and so we're changing.
This is Chief of Staff of the Air Force, General C.Q. Brown.
And we have a window of opportunity to change, to control and exploit the air domain to the standard our nation expects and requires from its Air Force.
Operating in the status quo can no longer be an option. The Air Force is looking to the future, and the future is quantum.
If we don't change, if we fail to adapt, we risk losing. We risk losing in a great power competition, we risk losing in a high-end fight, we risk losing quality airmen, losing budget dollars, our credibility, and aspects of our national security.
This is Quantum Possibilities, an Air Force podcast.
What's up? I'm Angel Orozco, Defense Media Activity.
Hello, I'm Tech Sergeant Dina Heitzman.
Dina, we're going to tackle quantum today. So where would you like to begin with that?
Okay, Angel, I'm going to need you to walk about 20 feet in said direction.
Oh, so we're doing experiments today.
We are.
All right. Do I bring the microphone with
Nope,
me?
you can leave it here.
All right.
Perfect.
Okay.
Now I'm going to have to ask you to just straight sprint into this wall.
And stop when I get to the wall?
Nope, just keep going.
Just keep going?
Yeah.
Okay. So you know that wall's going to win, right?
Yes.
Okay, I don't know the point of this, but okay, so let's say I do that. What after that? What's next?
Then you're going to do it again and again and again.
I'm not sure I'm enjoying this experiment, or I'm going to. Can I come back and can we talk about this?
Yes, of course.
All right, so with this experiment, and with the same result every time, what are we looking to do here?
So in a quantum world, the results may be completely different. And Dr. Kathy Ann Soderberg, a principal research physicist from the Air Force Research Laboratory in Rome, New York, can kind of explain that.
So quantum mechanics dictates the behavior of small particles, individual particles. So, you know, we're made of millions of atoms, but we follow classical mechanics. So if I jumped at a wall 1,000,000 times, I'd only end up hurt. But if I was a quantum particle and I jumped at that wall 1,000,000 times, there's a chance I could end up on the other side of it. So quantum mechanics is this very funny behavior that dictates how particles act, single particles act on a quantum level. And so you can use these features to your advantage for things like quantum computing, quantum networking, and other technology areas.
All right, so you kind of set me up for failure with that experiment, and I'm glad I didn't run into the wall and dislocate a shoulder or something. It would have been pretty cool, though, if I did slip through that wall somehow without getting hurt.
Yeah, that only would have applied if you were a quantum particle, but I don't think you are.
We can set the record straight on that. I definitely am not. Now, to give more of an image of what Dr. Soderberg was saying, her laboratory battle buddy, Dr. Paul Alsing, explains quantum in a way that is a little safer to my health.
If you imagine the letter W with two little troughs in it, and think of that as like a mini mountainscape, then we're used to the fact that if you rolled a ball down there from one side of the W, it could be anywhere in the V's shapes of the W, right? And that's what we call classical mechanics. It can have any energy you want. But what quantum says is this very strange thing that there are actually only discrete levels, like steps on a ladder, and you can only be on those levels and nowhere in between. And that's very, very strange. And as Kathy Ann said, that happens at the very, very small. So what that means is that in this W, if you're in the left-hand V part of it, and you're in one of these levels, if that was a physical billiard ball, you wouldn't be able to get to the other side, the right side of it, unless you hopped over the barrier in the middle. But quantum allows this weird thing that it has basically what's called a wave function that can extend through that barrier and then all of a sudden tunnel on the other side. And this happens all the time because this is basically how radioactivity works. This is how alpha particles get shot out from the nuclei, is that there is a Coulomb barrier, an electrostatic force that holds the the nuclei together, but every once in a while it can emit particles. So this is a very strange thing, and we've known about it now for about 100 years, but we're now trying to now exploit it to actually do things that maybe have technological implications.
Can you imagine being a scientist? What do you think they do all day?
Ideally, I think they walk into this like very white, sterile room and they have their white lab coats on and they're all just huddled around looking at calculators and lasers and just cool things that are around.
Pointing a bunch of lasers.
Exactly. That's exactly what I think of. Very stereotypical what you see on TV. So what does a day in your professional life look like? Is it, that 9 to 5 grind, or is it like very different, or just kind of like explain a snapshot of like what your day could look like?
I'm going to let you go, Kathy.
I'll do it from the standpoint of a researcher, since you said I could describe what my day could look like. So Paul and I are both group leads for the quantum team at AFRL in Rome. And so our days look a little bit different than the researchers that are actually doing the work. But everyone goes into work every day and there's this lab full of, of amazing state-of-the-art equipment, and we spend our days trapping these atoms and shooting lasers at them basically to manipulate them, to learn how to do new things with quantum mechanics like superposition and entanglement, and really learn how to harness those to be able to do novel things with the technology. It's really the best job ever. It's very cool to be able to do that every single day.
Yeah, so as Kathy said, you start out doing research, getting your degree, really diving into problems. And then as you move on in your career, what's nice is that you start being able to form a group. Like Kathy has the ION group, and I'm co-lead with Mike Fanto for the photon group. And then also with Laura Wessing for the quantum computing group. And then we also have another group that's a superconducting group led by Matt LaHaye. And you start to be able to basically build a research team, and you can let that research team go. And then your job is to focus that research group towards applications and getting results out. And then also what Kathy Ann and I do is then try to get these groups to talk to each other so that we're not just stovepiping. So there's a lot of administrative stuff being in between. You looking downwards, you got to get the group moving forward, doing things, getting results out. If you look up top, people want bullets for their slides that you can put on a slide and give me quantum in one bullet and don't go over the line and those kind of things. And it's important because, people up top are very interested in this and they want to promote it. So you have to do things to explain to them what this is in a way that they can understand. So it isn't just a bunch of gobbledygook and scientists running around, in their lab coats and their ivory towers doing things. And then, when you can, you read your papers at night and your wife says, why don't you do this during the day? And you're like, well, because there's not enough hours in the day.
Yeah, I guess another fun thing that Paul and I get to do, we get to help shape the direction that AFRL goes in for networking and computing. And that's a lot of fun because you actually have a say, in some sense, a very small say, in the larger picture of what the DoD is going to pursue.
How did you become involved with quantum research? I know it's a very niche field.
So I think I've always been interested in science, and I think I got interested in physics in middle school when we learned about atoms one day. I distinctly remember, that's the only thing I remember about middle school science, pretty much. And then in college, I was fortunate to have an opportunity to do some lab research. One of my professors had an atomic physics lab, and he offered me a job when I was a freshman. And so that kind of sparked my interest, and from there I decided I wanted to go to graduate school. I've just been going on in physics ever since, in atomic physics.
So the history of my life is that as a typical boy, I was into dinosaurs. And from dinosaurs, I went back for, well, where did they come from? And then that led me to, well, where did the Earth come from? And then I started reading when I was young, Isaac Asimov, iRobot and things like that. But he wrote scientific books for the layman. And he would say things like, well, we can tell the composition of a star far away. And I'm like, how can you do that without touching it? How do you know that? So that got me interested in science. And at a very early age, I said, that's it, I'm going to be an astrophysicist. And I decided very early, like from fourth grade, that's what I want to be. I want to study astronomy, where things came from.
Well, I guess you were kind of right on what happens in a science laboratory. That sounds like a really awesome occupation.
It does. It definitely sounds like a job I wouldn't mind having. Trapping atoms and shooting lasers at them. That sounds super exciting.
Speaking of atoms, I recently learned that they were almost overlooked because they are so small, and investors wanted nothing to do with something that wasn't relevant with life at that time in the 1920s.
If you were around in the 1920s and you're allocating budgets and you're one of these skeptics, you might say, why are you studying the atom?
This is world-famous American astrophysicist Dr. Neil deGrasse Tyson at the virtual $1 million International Quantum UTech Accelerator held in September.
It's so small you can't even see it. It's got properties we don't even care about. I'm a carpenter. All I care is that my wood atoms cut with my saw. All right? Why are you do this? Is a waste of money. This is some of the most brilliant people in the world dedicated to something that has nothing to do with anything in this world. People today, if they were alive back then, would be saying that to those scientists. Yeah, it would take decades, okay? 40, 50 years especially, before quantum physics would become manifest in the creation, storage, and retrieval of information. And so, back then computers are used by businesses, scientists, that's it. The public is still not thinking about it. Now, you cannot wake up in the morning without being touched by a computer in some way or another, and there is no creation, storage, and retrieval of information without an understanding of the quantum.
Neil deGrasse Tyson would go on to say that because of the investment in that research from the 1920s, that IT, information technology, now drives 1/3.
At least 1/3 of all the world's wealth. IT. And 40 years ago, would you have even imagined that? There are people employed in branches of our economy that would not have existed back then. So all I'm saying is sky's the limit. And I get to say that because I'm an astrophysicist.
That kind of sounds like what we're experiencing with quantum. There's a lot of people that want to invest in this new thing, but they're kind of skeptical about it because they just can't see the results yet. We see something super interesting and something that we really want to capitalize on, but we just can't see it through yet because we're still in that research stage.
You bring up a very good point because people keep talking about the valley of death for quantum, which the valley of death for technology always happens. There's great hype about it. And then the question is it always a promise, or is it going to turn the corner or actually get through the trough to where it's going to actually do something? In that sense, I think what you're saying is correct, that people are worried about, like, okay, well, when are we going to see this? And it's very hard to be able to say that. I hate to argue by analogy, but another field was superconductivity and actually Bose-Einstein condensation, which was known by Einstein and Bose way back in the 1920s, that you could condense all these particles into a big super ground state. And they knew it in 1920, and they knew that they could do it. And they spent 75 years trying to make it happen. And they tried all these different things, and people even got Nobel Prizes for stuff working in helium. And then it completely came out of left field that it happened in cold atoms in 1995. And that has revolutionized the whole field of like Bose-Einstein condensates that people are using. But they knew that it could happen. And that's the point that I was trying to make out. They knew that they could do it. They just didn't know how to do it. I think that's where we are right now. People tried for Bose-Einstein condensates for 75 years, trying many, many different things until they sort of cracked the problem. So I think that's going to happen with quantum. I think quantum is that we know that it can work. That's the thing that propels it. And that's why so many people are doing it around the world, is because they know it could work. But the engineering aspects are daunting. And I think that's where we are in quantum when we fight that battle, when people say, when are you going to give us something? And I would say that's almost impossible to say. But I think there will be a breakthrough, and when it comes, I think it will be really revolutionary.
Paul, you mentioned in one of the AFRL interviews about introducing a quantum aspect of a computer is kind of like introducing a pool without water
great.
with a little bit of water.
I don't know who said that, and I love that quote. I really do. The quote is that someone said to me a long time ago, maybe a professor or somebody, I don't know, and they should step up to say who did it, was that trying to teach someone about quantum computing is like trying to teach someone to swim without water in the pool. It's like trying to teach someone to swim without water in the pool. And these new machines that are coming out, even though they're prototypical, give us a little water in the pool to be able to say definite things one way or the other. And we're actually in an area of co-design where the algorithms are driving the machines, which then break the machines. They then force a redesign of the algorithm, and they feed back and forth in each other. Very much like the early 1990s when we were building supercomputers out of separate PCs. Having these computers right now that are out there by IBM, Google, Rigetti, IonQ, all these computers that are just starting to get out, you know, to be honest, we didn't think a few years ago that we'd actually see these in our lifetime. So to me, that's what I call the puddles. They're not quite a pool yet, but they're puddles, and we get to splash around them and see what works and see what doesn't work. So a lot of this is that you're not going to solve this with theory and simulation. It's the Nike approach, just do it. And that co-design of, well, let's try something, let's get some theory, let's see if we can affect what we actually do experimentally. That's the approach that, like, a lot of people are going. The Department of Energy is going that way with co-designing these devices. The big companies have got their own approaches, but it's great to see these things out on the market. They're still, I would say, still research devices. They're pushing them heavily as trying to get them to production devices. But I think people realize right now that they're stepping stones. Just the way, remember, now I'm old enough to remember that, you know, there was the Atari, and then there was the Commodore, and then there was the Mac SE, right? And the computers got progressively better. I think that's what we're hoping to see, not just with computing, but with these other technologies, the timing and the sensing applications and the communication as well.
Dina, we've barely scratched the surface of what quantum is. We've talked about atoms, quantum particles, and prototype quantum computers, but then there are still things out there like qubits, which is a quantum bit and is a physical entity, unlike its counterpart, the classical bit.
Yes, and there's entanglement, superposition. It's really too much to get into in one session here. I think the overarching question for us is, how is all of this going to better serve the Air Force? According to Dr. Michael Haydick, the Information Directorate Deputy Director at AFRL, he says quantum will lead to technologies that will transform the warfighting domain in revolutionary and unprecedented ways. Here's Kathy Ann and Paul elaborating on that thought.
There's 4 main areas of quantum. There's timing, which is make better clocks. There's sensing, which is self-explanatory, make a better sensor. There's communication and networking, which is, you know, it's not exactly the internet, but it will be a complementary layer to the current internet that will probably provide an additional level of security, but also brand new ways to communicate. And then quantum computing, which will allow you to compute things exponentially faster in some cases.
What about a technology like GPS? Which of these 4 quantum areas could affect that?
Yeah, timing and sensing. So if you're able to combine the work of quantum timing and sensing, then you can push for things like GPS-like accuracy in GPS-denied or degraded environments. So the whole field of quantum timing is trying to make a better clock. And for the Air Force in particular, you know, we want to reduce the form factor, because the best clock in the world you can find at a place like NIST, the National Institute of Standard and Technology. It's a tabletop device that requires an entire room to run, but it's the best clock you can get. You know, it's better than the atomic clock standard. It's so accurate. And so if you can miniaturize that type of accuracy and put it on in a form factor that's amenable, say, to putting on a plane or a ship or sending with the warfighter, and you combine it with these quantum sensors that people are researching, then you can get GPS-like accuracy in places where you can't get the GPS signal necessarily.
Big one, defend west.
Roger that. 10 miles, he's back
Right
up
now,
the
offer
road.
knows 5 miles.
Tax one again.
The quantum possibilities seem kind of limitless, and the great thing about it is the Air Force doesn't have to do this alone. They're hosting events like the $1 million International Quantum UTech Accelerator that I referenced earlier, where there were over 200 quantum-focused submissions from universities around the world.
The event was done in part with the AFRL's new Innovare Advancement Center, which is an open facility dedicated to researching quantum networking and computing. And of course, Kathy Ann and Paul were involved with this as well.
But it doesn't stop there when it comes to spreading the wealth, so to speak, in accelerating quantum.
You know, along with that, we've had some other events too. There's been some small business calls for small businesses to get more involved in this research to help push the technology forward. And most of these have been for, I would call them enabling technologies. You know, the quantum is one thing, but then there's a lot of underlying systems that you need to get the quantum systems to work well. And we often call those enabling technologies. So it's really a push to get the enabling technologies to where they need to be and available to the researchers so that we can continue to push forward and make advances in quantum.
The only thing I would add to that, I firmly believe that, you know, this is a very interdisciplinary field, and you get results by spreading the funding as much as you can. It's not just the big established people who do great work, but if you spread this out, applications and new ideas are going to come from everyone jumping in the field, and that's how progress works. And so I think these things like the challenge that we just had is a good way to sort of spread that out to as many people as possible, and not just go to the, I'm not denigrating anybody, but, you know, the big people, you know, the MITs, the Caltechs, you know, they're always going to do great work and they attract the best people. But I think it's really, the advancements are going to come from people playing with this stuff across the field at other universities and small companies as well. So we're hoping that, and I think the world is hoping that, as you know, someone's going to come up with some bright idea, and you don't have to be a physicist. You know, just have to be someone that can see how to take the laser and make it scan your food in the grocery store. That's the unique thing that's going to make the next Google or the next Facebook.
I never thought I'd say these words, but I'm kind of jacked to see what will come from quantum in the future.
Hopefully the near future. And thank you so much for talking with us, Dr. Kathy Ann Soderberg and Dr. Paul Alsing.
Thank you. We appreciate it.
Yes, thank you both for giving us this opportunity.
Trust me, the pleasure was all ours, and thanks for the open invitation to come check out your laboratory.
Definitely.
Yes.
You're more than welcome. Please come check it out. It's awesome.
Thanks for listening. This is Quantum Possibilities, an Air Force podcast. I'm Tech Sergeant Dina Heitzman.
And I'm Angel Orozco. Before we take off, we want to leave you with some thoughts from Dr. Will Roper, the recent Assistant Secretary of the Air Force for Acquisitions, Technology, and Logistics. And by the way, he's also a physicist.
Recently, he sat down for an Ask Me Anything live YouTube event where he stressed the wide-ranging possibilities of quantum and something he calls Q-Day.
When we kicked off Quantum Accelerator between the Air Force Research Lab and AFWERX, we wanted to shine a spotlight on all of the other kinds of quantum capabilities that we are very interested in that get very little limelight, like quantum sensing, single photon detection, being able to look around walls. I mean, that's superhero stuff. I want to be able to do that. And so do our special operators. Well, that technology's, it's not too far away with investment. Or what about quantum gravimeters to detect things that are heavy? So there's a whole field of quantum sensing that's not getting the kind of love that quantum computing can be. And the whole idea with our quantum accelerator was to set a target for what we call Q-Day in the Air Force, which is the day we operationalize that next quantum effect. That's the reason for going into deep tech.